Let's start working on section 9.3, double angle identities and reduction formulas. We are going to skip what are called the half angle identities, so we're going to begin by deriving a few more of these trig identities, and I'm going to put on the screen here a sheet that I normally pass out for exams because I won't ask you to memorize all these identities. You can refer to this sheet on the final exam and on our last test. And this summarizes all the ones that you want to have at your fingertips. And it's not all the identities. There are other things you have to have memorized. These are the ones you don't have to have memorized. We've already derived the ones up at the top. Those are all the sum and difference identities. We're now going to talk about this lower left corner. These are called the double angle identities. And on this sheet, just for reference, I have some more listed here. These are called the half angle identities. That's what we're going to skip, okay? We're not going to talk about those. So let's start talking about the double angle identities, and we're actually going to build these off of the sum identities for sine, cosine, and tangent. So let's go ahead and do that. It's actually not too hard to derive these from scratch. So first, let's think about sine at 2 theta. We're going to derive a double angle identity for sine. And the way we derive this is we're going to think of 2 theta as theta plus theta. Theta plus theta is 2 theta. And what that does is that allows us to invoke the sine of the sum identity, sine of alpha plus beta, we call it on our formula sheet, which is sine of alpha cosine beta plus cosine of alpha sine of beta. So all I'm going to do is plug in to that identity. I'm going to write it below here. And instead of writing alpha and beta each time, I'm going to write theta, because we have just a single angle theta here. The alpha is theta, the beta is theta. So I get sine of theta cosine of theta plus, for the second term, I'm going to get cosine of theta sine of theta. So for this theta plus theta situation, I end up with 2 terms that are actually like terms, sine theta cosine theta. The second term is also sine theta cosine theta. So I can combine them, I can add them together, and just write that as 2 sine theta cosine theta. And so if I write sine 2 theta equals 2 sine theta cosine theta, I have my double angle identity for sine. Okay, now let's do the same thing with cosine. Let's take cosine 2 theta and think of it as cosine theta plus theta. And we're going to bring into the picture our cosine of the sum identity, which we write as cosine alpha plus beta. And referring to my identity sheet or my notes from the previous section, I know that's cosine of the first, cosine alpha, cosine of the second, cosine beta, minus sine of alpha, sine of beta. So I'm going to do the same kind of thing we did with sine. I'm going to set alpha equal to theta, beta equal to theta. But now I'm plugging into this cosine of the sum identity. So I'm going to get cosine theta, cosine theta, cosine alpha, cosine beta is cosine theta, minus sine alpha, sine beta becomes sine theta, sine theta, which is just cosine times cosine is cosine theta squared. We'll use the shorthand, cosine squared theta, minus sine theta squared. Again, I'll use the shorthand, sine squared theta. So we have cosine of 2 theta has an identity that looks very different from the double angle identity for sine. We're getting cosine squared theta minus sine squared theta. And it doesn't seem surprising to me that these identities are very different for sine and cosine, because the sum identities, the alpha plus beta identities for sine and cosine, were also very different. Now what I'm going to do is I'm going to actually obtain 2 more versions of the double angle identity for cosine. And what we can do is we're really going to take this in 2 different directions. What I can do is I can replace cosine squared theta in this double angle identity for cosine with 1 minus sine squared theta. I'm really using that relationship that comes from our Pythagorean identity, sine squared plus cosine squared equals 1, right, for any angle. So I'm going to go back to cosine 2 theta equals, I'm going to replace the cosine squared with 1 minus sine squared theta. And I still have a minus sine squared theta on the end. And what this does, it allows me to write the right-hand side with sine only. And so I get, what do I get here? I can combine like terms. I have 1 minus 2 sine squared theta. That's cosine 2 theta. And that is, for better or worse, another version of the double angle identity for cosine. And now we're going to come up with a third version, because we just can't get enough of this. I'm going to take that same original double angle identity for cosine, and I'm going to replace, I can do the reverse here, sort of. I can replace sine squared theta with 1 minus cosine squared theta. And let's see if I can fit this in here. I'm going to have cosine 2 theta is equal to, now I'm going to leave the cosine squared theta there. And I'm going to replace sine squared with 1 minus cosine squared. Now I got a minus sign. 1 minus cosine squared theta, I'm going to write. And the tricky part here is we're replacing sine squared with this quantity, and because it comes behind a minus sign, I need to group that together. And I'm going to have to distribute the minus sign. So it becomes cosine squared theta minus 1, and then I get minus a minus plus cosine squared theta. And again, I can combine like terms. Here I end up with 2 positive terms. Cosine squared theta plus cosine squared theta is 2 cosine squared theta minus 1. And that's equal to cosine 2 theta. So notice it's a little bit different here. We have a positive 2 cosine squared theta minus 1. When we did the same kind of trick with sine, we ended up with a positive 1 minus 2 sine squared theta. And these are the 3 famous forms of the double angle identity for cosine. On our formula sheet, we have 1 line for sine of 2 theta, but for cosine of 2 theta, we have 1, 2, 3 lines, because we have 3 versions that we can pick and choose as we like for various situations. Now I want to do one more. I want to derive an identity for tan 2 theta. which is also I can think of as tangent theta plus theta. And so I'm going to rely on my tangent of alpha plus beta identity. And remember, that was we derived that, I think, at the end of the last section. It was a fraction, tangent alpha plus tangent beta over 1 minus tangent alpha times tangent beta. So here I'm going to replace both alpha and beta with theta and copy down the right-hand side of that identity, tangent theta plus tangent theta over 1 minus tangent theta, and I can combine like terms. Tan theta plus tan theta is 2 tangent theta over 1 minus. Now above I'm adding 2 tangents, so I get 2 tan theta. Below here I have 1 minus the product of 2 tangents. I'm multiplying them, so I get 1 minus tangent squared theta. And there's tangent 2 theta equals that guy. Okay. And so that's also on our identity sheet here in the lower left corner. These are our double angle identities. Now before we do some problems, I'm going to take this a little bit further. So there's our summary of identities. We start with sine 2 theta, cosine 2 theta. We have 3 versions. And then we ended up with tan 2 theta identity. I just want to derive a couple more formulas called the reduction formulas. And I don't actually have these printed on the formula sheet because it's really not too hard to obtain these from some of the identities we already have. So I almost don't think of them as totally independent formulas, but I want you to see this idea that we can take cosine 2 theta equals 1 minus 2 sine squared theta. That was the second version, right, of our cosine 2 theta identity. And what we can do here is we can isolate sine squared theta. So what I'm going to do is I'm going to take this negative 2 sine squared theta over to the other side, add it to both sides. I'll have 2 sine squared theta. I'm going to leave the 1 where it is. And then I'm going to subtract cosine 2 theta from both sides. So I end up with 2 sine squared theta equals 1 minus cosine 2 theta by rearranging a bit here. So I wanted a positive sine squared term. And to isolate the sine squared, I'm going to divide both sides by 2. And I get sine squared theta equals 1 minus cosine 2 theta over 2. So I almost hate to even put this in a box because it's not too hard to obtain this from the cosine 2 theta equals 1 minus 2 sine squared identity. All we did was isolate sine squared. But it turns out this is a convenient form, and it's used in calculus class. When you guys move on to calculus, your calculus teacher's just going to pull this out of the back pocket at some point and make use of it. Let's keep going. We're going to do a couple more of these. We're going to take cosine 2 theta. Again, that other version, in terms of cosine squared, it was 2 cosine squared, a positive 2 cosine squared minus 1. and we're going to think about isolating cosine squared in this identity. Now, here, I'm going to leave cosine squared on the right because it has a positive coefficient. I'm going to add 1 to both sides to get cosine 2 theta plus 1 equals 2 cosine squared theta. And now, in this form, I'm going to divide both sides by 2. And I get cosine 2 theta plus 1 over 2 is cosine squared theta. But I just want to write that. I'm going to recopy it here on the side with the cosine squared on the left, so we have some symmetry with our sine squared. And because I'm adding two positive terms in the numerator of the fraction, I can put them in either order. I'm going to write the 1 first. 1 plus cosine 2 theta over 2. You know, the only reason to do that is it matches the sine squared. And I'm just going to put a dotted line around this because I don't think it's really its own brand new identity because it just fell out of our one of our versions of our double angle identity for cosine. And one more, we're not done yet. I'm going to take tangent now. And I'm going to go right to tangent squared. And I'm going to take a little twist. I'm not actually going to use the double angle identity for tangent. I'm going to use what we already have here for sine and cosine. Tangent squared theta I can think of as sine squared over cosine squared. And I'm just going to replace the right-hand side of my first box that I put a dotted line around. And let's see, that's sine squared, so 1 minus cosine 2 theta over 2. And I'm going to divide by cosine squared. I'm going to use the right-hand side of my other dotted line box. 1 plus cosine 2 theta over 2. And let's just convince ourselves that this division I can invert and multiply by that denominator fraction. So that's the same as multiplication by 2 over 1 plus cosine 2 theta. I just want you to convince yourself that those 2's are going to cancel out in this calculation. We end up with 1 minus cosine 2 theta over 1 plus cosine 2 theta. It never ends. These identities go on and on. And that's an expression for tangent squared theta. And I don't think this one's so obvious. It's sort of a new surprise. And I'm not going to require that you use this. You can use it if you want, because we can always work around it. We can always obtain sine and cosine first before going to tangent, I think, in the problems we're going to see at least. So I just want to have that on there for the record. And so here are our reduction formulas. I'd say the two dotted line boxes are probably going to be more useful in your futures. And that's the end of this portion of the video. We're going to start using these now in the next part.